Howdy. The purpose of this video is to talk about magnetic domains in ferromagnetic materials and what is the difference between soft and hard ferromagnets. Now, there was already a video that talked about the origin of magnetization, so if you haven't seen that yet, I would recommend going and viewing that. Now, really the heart of the matter is that we have different magnets that we'd like to serve different purposes. So a magnet in a generator needs to have be a hard, permanent magnet. It needs to have some particular magnetic direction, and we want it to stay that way. And we want as much magnetic field as possible coming out of that. A transformer is the absolute opposite. It needs to be magnetic, but it needs to be very soft. It needs to switch its magnetic direction back and forth very readily, because usually we're using these with an alternating current, so the current direction is switching, so we need that magnetic field to switch as well. A magnetic storage hard drive is somewhere in between. We need it to have enough energy that it doesn't flip spontaneously, but we don't want it to be too hard because we need to come in here and we need to be able to rewrite an individual bit and say, you're going to be spin this way, and then I might need to erase it and have that pointing in the other direction. So again, in all of these cases, I'd like to be able to control something about the direction of magnetization in the system. So we're going to start thinking about iron. And we're going to talk about the magnetic behavior of iron. Now, iron is interesting because if I take a lot of iron shavings, that's what all of these are here, all these little bits, they're going to be very responsive to a magnetic field. And they tend to align themselves along that magnetic field. So here I have a hard permanent magnet. So this is not iron. Not iron. And I have iron shavings. However, if I take individual iron objects, think about iron nails, for example, I don't necessarily think of them as being magnetic. They don't really seem to interact with each other very much. So there's something different about that. Now, you might think, okay, well, maybe it has something to do with the magnetic order of the individual atoms in the system. Iron is well below its Curie temperature, well below the ordering point. So all of the atoms are aligned with their neighboring atoms. So iron at room temperature is a ferromagnet. But why don't two iron nails seem to interact when I have them touch each other then? And the answer is that all of this whole iron is not necessarily pointing in the same direction. There are small regions. Within that region, all of the magnetic moments are pointing in one direction. And so this is what I call a domain. So a domain is a region within a crystal that has all of those magnetic moments aligned in some particular direction. So just to point this out, this can all be in one single crystal of iron. So the lattice, the atomic spacing, is continuous throughout. So the atoms are all ordered. There is a separate subdivision. So within the single crystal, I have different magnetic domains. And within each individual domain, all of the atoms are aligned and pointing in the same direction. There's then some sort of boundary, some sort of domain wall, and then I have a region that the atoms are pointing in a different direction. And they'll do this to minimize the overall energy of the system. So what the result is at room temperature, in a single crystal of iron or in a polycrystal of iron, anything like this, iron nail, for example, all of the atoms are aligned with their neighbors. However, the domains are arranged in such a way that they're going to cancel each other out. So there is no net magnetic, there's no net magnetization for this particular iron, right? So because I have some magnetic moments this way, this way, this way, this way, the net magnetic moment is zero. There's no net magnetic moment. So magnetic domain structures can take on an incredible diversity of patterns and arrangements, and it's all due to this fine interplay between different energy terms within the material. And I just wanted to show you a couple examples of these. Over here we have some very thin layers of gadolinium and iron, so alternating. and these have these relatively maze-like structures where one color is going to be pointing out of the plane, and the other color has the magnetization pointing into the plane. Something else, this is a very hard, permanent rare earth magnet, has a very different structure. And these are amazingly fractal-like patterns, right? So the magnetic domain structures can take a wide diversity of arrays in different magnetic materials. Okay, so let's come back to the picture of the iron and get to the heart of it. So if there's zero external magnetic field, all of these domains are going to be arranged in such a way that the magnetization of the material also is zero. If I start increasing the external magnetic field, then I start arranging those domains so there's more and more pointing in some direction. So let's say I apply some external magnetic field in this direction. What is going to happen is that the domains that line up in that direction are going to start to grow. They're going to get a little bit bigger at the cost of the surrounding domains. And so the net magnetization in this system, if I'm at some external magnetic field like that, is going to start increasing. And at some point, I will saturate. So this is what I call the saturation magnetization. And at that point, I've rotated and I've grown all of these domains such that the whole crystal is now pointing in this one direction, aligned along the magnetic field. So different materials can have different behaviors in, this is what we call a magnetic hysteresis loop. So a soft ferromagnet, something like this iron, is going to increase its magnetization, and then it'll decrease its magnetization and come back essentially through that origin once again. And so what that means is it doesn't take a lot of energy to flip from magnetization going one way or magnetization going the other way, right? So this is going to be very different from a hard permanent magnet. So if I think about a hard permanent magnet, it takes some, this is probably not the best way to try it. Let me try one more time. It takes some magnetic field to start aligning the domains in a particular direction. Eventually I'll saturate as well. If I start removing the field, I'm going to have a residual magnetization in the material when I have zero applied external magnetic field. And I have to apply a magnetic field in the opposite direction to get that system to switch. And so what I end up coming up with is what we call a magnetic hysteresis loop. And so this is describing how much magnetic field does it take to switch the magnetization one direction versus another direction. So those hard permanent magnets in the generators, I need to have a large hysteresis loop, because the larger this area, the more energy it takes to reverse the direction. And if I'm thinking about a generator, I don't want the direction of those permanent magnets to reverse at all. The hard disk is going to be somewhere in between. I need to have relatively hard to switch because I don't want those magnetic bits to switch spontaneously, but I can't have it too hard or else it would be too difficult for me to rewrite what's on that magnetic disk. So this is kind of at the heart of it, but the thing that I want you to remember the most here is that all of this is, all of this magnetization behavior on the bulk level is caused by the reorientation of the different domains on the microscopic level. Again, this is sort of micron level, and if I was able to zoom way, way in, I could again see all these atoms that within a domain were all arranged in the same direction. Okay, so in a summary, ferromagnetic materials tend to form domains. There are regions in which the atoms are all have an aligned magnetic moment. These domains can cancel each other out and result in no net magnetization. So I think about iron nails, they don't really tend to interact with each other because there's no net magnetization from either of those iron nails, even though it's well below the ordering temperature. So I know the atoms are aligned on the atomic level. Finally, permanent magnets that have domains that are difficult to flip and rotate and move around, those are our hard permanent magnets.